move on to the next section. I'm not going to go directly from the book. I'm going to go from my notes, but it is the next section up through page about 184 or so, talking about molecular geometries. Molecular geometries. It's kind of cool because we're actually moving into three-dimensional space now with our molecular geometries. Okay, so again, I'm not following the book strictly. It may help you to have the book out in front of you. I'm going to follow my notes. And there's many different ways of looking at VSEPR. That's how it's pronounced. I was teasing before the quiz. It's written VSEPR and pronounced VSEPR, which is not literally the order of the letters, right? To be VSEPR, it should be VESPR. We say this VSEPR, but we recognize it's not written, spelled correctly, because this is an acronym that stands for Valence Shell Electron Pair Repulsion. Valence shell electron pair repulsion. Now we're going to be looking at covalent molecules where there is a bond that's formed. And we're going to treat these bonds as if they are, well, frankly, as if they're lines. And what is the angle between the bonds? Like, we're going to actually look at different molecules, and based upon their construction, we're going to compute their geometries. What is the shape of that molecule? If I could, again, to use the analogy, get on Miss Frizzle's school bus and go down to the molecular level, what would I see if, let's say, atoms were actually this size in front of me? There's several different approaches, several different techniques on building this up. I may do my own presentation. I may go and ask, look for Tyler, or a couple of the chemistry professors that I view online at occasion to help me out on how to teach it, and look at their presentations and maybe share those with you as well. So this will be the first shot. Mr. Baker's going to take first shot rather than giving Tyler first shot and me doing cleanup. I'll do first shot and let him do cleanup on valence shell electron pair repulsion and molecular geometries. Sounds intimidating, but there's just a couple of principles that you really need to understand. First of all, we're talking about geometries. We've already mentioned in here that we're moving from a two-dimensional to a three-dimensional space. Now, if I'm trying to draw something on this board, you recognize that it's two-dimensional, right? It's got height and it's got width, but it doesn't really have depth. I'm taking something, I'm drawing it in two dimensions. And that when we recognize that real life is not two-dimensional, we don't live in flatland, right? We live in a three-dimensional space, that molecules are actually three-dimensional. So while I try to draw them on a flat board, which is two-dimensional, my two-dimensional drawing is representing a three-dimensional item. And so there's certain techniques that we use to try to communicate the idea of three dimensions over two dimensions. I'll do that up front and just give you those basic symbologies or basic symbols. We're going to learn in just a moment about a tetrahedron. Tetrahedron shape, it's this shape right here. It's got a center molecule and 4 attached atoms to the center atom to form a molecule. If I were to draw an example of this, just like we said before, if I have a certain molecule that has a certain center atom, the pivot atom, I'll call that the central atom. Do you remember how one of the atoms becomes the central atom from your Lewis structure? Okay, so it has the least number of unpaired electrons. Unpaired electrons. I sometimes say unbonded electrons, but I mean unpaired electrons because at the atomic level, they're all unbonded before they form a molecule. So it's technically the highest number of unpaired electrons. And in the case of this molecule, I'll submit to you that this is something like a methane molecule, a CH4. Okay? So we start with a CH4 molecule. We'll draw the Lewis structure for my methane, my CH4. By now, you should look at that and say, carbon, it's column 4. Hey, I know that if I've got a column or nitrogen or something else from column 4 or 5, it's probably the center. It's probably the hub atom in this molecule. Oh, and I've got 4 hydrogens. Doesn't that make nice symmetry? 4. I've got 4 openings and 4 attachments. This is going to be easy. I've got a carbon in the center because it has 4 unbonded electrons. Hydrogen has 1 unbonded electron. So there's my 4 for carbon. My first hydrogen is here. It's got 1, 1, 1, and 1. Now those electrons are shared. And there's my Lewis diagram for CH4. But this is a two-dimensional drawing of a three-dimensional object. If I asked you right now, what is the angle between the lines that represent the bonds between this hydrogen and this hydrogen, what would you say? How many degrees are there between them? Okay, so there's 4 right angles here, right? They're all 90-degree angles. So in a Lewis two-dimensional drawing, all of those atoms are 90 degrees apart, the bond angles. And the bond angles in my model like this are these sticks. These sticks represent the bond angles, or represent the bonds, and the angle between them represents the bond angle. So in a two-dimensional drawing, this would look like 90-degree angles, so it would be the 4 coordinates like on a compass, my center, and north, south, east, and west. But in 3 dimensions, this is what that molecule looks like. Does it look like a compass? Does it look like it's got a north, south, east, and west anywhere? It doesn't, right? What we're doing when we draw the Lewis structure like this is we're showing that those different bonds are trying to be as far apart as possible. And to be as far apart as possible as they can be in 2 dimensions is 90 degrees. However, when we go to a 3-dimensional drawing of the same molecule, it looks like this. Okay? The different symbology that we use to represent its space in the z-axis. Think of this as, you know, if I were to draw a graph up here, I would say, which is my x? Well, this is my x. This is my y. But for 3 dimensions, I need a z. And the z is this axis that comes right out of the origin, straight out towards us, and straight back in that way. So I can then plot things in 3-dimensional space instead of 2-dimensional space. If I draw the CH4 molecule in 2-dimensional space, it looks like this. If I draw it in 3-dimensional space, it looks like this. Now, if I try to duplicate that, see, let me try to duplicate as best I can. This is what we get, right like that. See the drawing up here on the board? This drawing represents this molecule oriented in this way. What do we have? We've got the center carbon, straight up hydrogen, and down at this angle, the other hydrogen. These are in a plane. If you came to the side and looked right here, the carbon, this hydrogen, and this hydrogen are in a plane. Just like the plane of the board. They're parallel to the board. Okay? Now, from this center, as I go down to this molecule, you see that I'm coming away from the board slightly. You see that? It's coming closer to you and away from the board. I draw this molecule, or this atom down here that's slightly towards you by using this shape, this long triangle. This symbol represents that it's coming out towards you in the z-axis. It's coming out in this direction. What do you suspect that the dotted line means? This one in the back that's going away from you. So in this representation here, this carbon, this hydrogen, and this hydrogen are in a plane. This hydrogen down at the bottom is coming out towards you, and this hydrogen in the back is going away from you. And that's how you read the 3-dimensional VSEPR diagram and figure out the geometries from this. Now again, we're using CH4 as our example molecule, but this is any molecule where the central atom has 4 connecting points. 1, 2, 3, 4 connecting points. Okay? Which frankly is going to be a lot of our atoms, right? A lot of them are going to have 4 connecting points. Why? Because we're talking about 8 valence electrons. 8 valence electrons means you're going to have 4 connecting points, each one being a pair. The question then becomes, is it a bonded pair or is it a lone pair that belongs to that molecule? And we'll get to that as we move along. But what I want you to know right now is for a CH4 molecule, or for any molecule that has a central atom and 4 bonded other atoms, it's going to have that same identical geometry. They're all going to look like this. Now the question is, the angle in 2 degrees is 90 degrees. What is the angle in 3 dimensions? In 2 dimensions, it's 90. because 90 represents every bond getting away from each other as far as they can be away from each other. If this bond right here decided, I want to get away from this guy down here and I'm going to slide up, then it's decreasing its distance from this one. And it would repel it and push it back down. So if you move any one of these, the forces are going to repel and they're automatically going to go boop, back out to symmetry. Perfect symmetry of, in 2 dimensions, 90 degrees. What does that look like in 3 dimensions? It's 109 degrees. The angle between every bond is 109 degrees. So here's the deal. If you draw a Lewis structure, and your Lewis structure has a central pivot atom and 4 bonded atoms to it to form the molecule, the angle between the bonds is 109 degrees. That's your memorization point, okay? How do I draw an atom that has a central atom and 4 bonded atoms to it? Like this. Its shape is called a tetrahedron. Its shape is a tetrahedron. And so, if on a quiz or exam there was a molecule which had a central pivot atom and 4 bonded atoms to it, you know right away it's a tetrahedron. And you know right away the angle between every one of these bonds is 109 degrees. If you want to dig deeper into it and find out why is it 109 degrees, beyond just the simple fact of perfect symmetry, well, that's not in the scope of this course, okay? So 4 connections to a central atom, they repel each other so that there's perfectly 109 degrees between every bond. And hopefully, I mean, my models aren't perfect, but hopefully you can visualize that every connected atom, every external atom in this molecule is equally distant from every other one. It's 109 degrees between here and here, here and here, here and here, here and here, here and here. I mean, they're all 109 degrees. Because if anybody moves, they simultaneously get repelled by the one they're coming closer to, and they've got less force against the one they just moved away from, and the forces would push them right back to perfect symmetry immediately for 109 degrees. Okay? Now, that represents a 4 connecting to form a molecule. 4 attachment points for a molecule, and this is our tetrahedron. The next shape is also based on a tetrahedron because we're going to have a central atom that has a valence desire of 8. However, if rather than CH4, I said we are dealing with, not to be confused with ammonium, but ammonia of NH3. Let's draw the Lewis structure for an NH3, an ammonia molecule. What's the valence, number of valence electrons on nitrogen? Column 5, okay. So I'm going to draw my nitrogen here, and this is where it becomes, as a strategy, well, I told you before, for the column 5 elements, put your paired electrons on the top. If you have 5, just put the 2 on the top. Just always, if it's nitrogen, phosphorus, that whole column, actually nitrogen and phosphorus, the only 2 you're going to have to really worry about, put the 2 on the top. Then, I've got 5 total, right? So I'm going to add 1 on each of the other cardinal positions. So I have 2 on the top, and how many, looking at this, how many atoms can I bond to this now? How many atoms am I going to bond to this nitrogen to form a valence of 8? How many connecting points do I have open? 3, right? So 3 atoms are going to come into here to fill this up, and that's what ammonia is. It's NH3. So if I bring in hydrogen here, and here, and here, okay? Hydrogen has a valence desire of 2. Nitrogen has a valence desire of 8. And by sharing these electrons, they are all satisfied. Their valence desires are fulfilled, right? 2, 2, 2, 8. Everybody see that? Okay, so I've just built my NH3 molecule. Now here's where it gets a little bit different, because if I look at my central atom has 4 connecting points, but it only has 3 things connected to it because of this pair. Okay? Now, if this had been another hydrogen, and if we lost an electron, that would basically be ammonium, right? We could then come back and say, hey, this is going to form a tetrahedral because it has 4 connected to it. It's going to be this same shape, but that's not what we have. We have an unbonded pair and 3 bonded atoms. So we get a shape that's a little bit different than this. Do you see that it's based on this? Again, because it has 4 connecting points to the nitrogen, it's based on this, but it's not this, because rather than having 4 atoms connected, we only have 3 atoms connected. And so the shape is slightly different. And this is what it looks like in my 3-dimensional model. In these 3-dimensional models, the double pair white balls, they represent an unbonded electron pair. Okay? Now, see the board right here? This is what this looks like in 3-dimensional space. This is what it looks like in 2-dimensional space. Now, in 3-dimensional space, you see that the only difference between these two that you can see is that on this case, I've got 4 bonded atoms, which means on this connecting point here, I have an atom connected. In this case, there is no atom on that point. It's an unbonded electron pair. Okay. Now, in terms of logic, when we develop our 3-dimensional models, the thing you have to remember is that an unbonded electron pair has more force, more repulsion. Valence shell electron pair repulsion. Okay? An unbonded pair up here has more repulsive force than a bond. Okay? Now I said that the tetrahedron forms because all the forces pushing away are perfectly balanced and perfectly equal, and so they form a perfect 109 degrees. However, on this one, if I have the same shape, but I replace this atom with an unbonded pair, and the unbonded pair has more repulsive force than the bonds, what's going to happen? What's going to happen if this top point is pushing away more than this top point? Hopefully you see that if I were to take this model, pull the top off and put an unbonded pair of electrons on there, and I told you that the unbonded pair has more force, that what's happening is relative to a tetrahedron, this has more force squeezing these atoms down. They're getting pushed away from here more than they're being pushed away from each other. The net effect is these bend down and get closer to each other. Slightly. Not terribly, but slightly. Slightly bent down. And so what happens is, rather than being a perfect tetrahedron, this starts to look more like a tripod. Because this perfect angle here, if this had been another atom, this would be 109 degrees. But since I replaced it with an unbonded pair, it's going to push down, push everything else away from it slightly stronger. And what ends up happening is that the angle between the bonds, not the angle between the unbonded pair and a bond, but the angle between all the bonds, now becomes 107 degrees. 107 degrees. So drawing this in 3-dimensional space, I've got a nitrogen here, I've got an unbonded pair here, and I have over here a hydrogen. I still have a hydrogen coming forward, and I still have a hydrogen going back. So it looks remarkably like the last one. But rather than these all being 109 degrees apart, these are all 107 degrees apart. And whereas the 109 degree separation was known as a tetrahedral, the 107 degree apart is known as a pyramidal. Okay? So 3 bonded atoms with an unbonded pair. Its shape is based upon a tetrahedron, but it's not a tetrahedron because it has an unbonded pair rather than an atom on the top, and that squeezes everything down 2 degrees. Squeezes it down. Squeezes it down. Why? Because this unbonded pair pushes away on these bonds stronger than a bond would. So forming the pyramidal, and I think of tripods. Every time I see a pyramidal, I think of a tripod. It's a tripod with a camera on top. Okay, so think of it like that. It's not perfectly 109. It's holding it up a little bit higher because the legs are pushed down from this unbonded pair. A pyramidal. Well, now we've got one more molecule that we can go to based upon the, actually two more, but next step on this. Let's say that rather than having one unbonded pair, we end up with two unbonded pairs. We have a central atom that has a desire for 8 valence electrons, which means it has 4 connecting points. However, rather than having 4 atoms, or rather than having 3 atoms, it only has 2 atoms. See? I've taken the 4, and I've replaced one of the atoms with an unbonded pair. Now I've taken this pyramidal, and rather than having 3, I only have 2, and I've got 2 unbonded pairs. Okay? This molecule looks a lot like water. Let's go ahead and draw the formula. It's H2O, right? H2O. As I try to draw the Lewis structure of H2O in 2 dimensions, I've got oxygen, which has 6, and hydrogens, 2 of them, which are going to bond to the unbonded or unpaired electrons there. And that's my 2-dimensional Lewis structure for H2O, for water. Okay? This is 2-dimensional. Here's what it looks like in 3 dimensions. Okay? My 3-dimensional Lewis structure. How am I going to draw that in 3 dimensions? Well, we're going to go ahead, just as we've done before, we're going to put the unpaired electron in the plane of the board. If I hold this in the plane of the board, it looks something like that. So if I draw my oxygen, and I put an unbonded pair here, and an unbonded pair here, then I have a hydrogen that's coming out of the board towards me, and a hydrogen that's going back in the board in that direction. So this is my water molecule. Okay. Now we need to figure out what's the angle between these 2 bonds. Remember, the bond angle is the angle between the bonds. Now, let's use the logic. This was 109. This was 109 with 4 attached atoms. But when I went to another molecule that had the same central atom that had an 8 valence desire, 4 connecting points, but had 3 atoms in an unpaired or unbonded pair, we said the unbonded pair pushed harder away, repelled the others more, and so it went from 109 degrees to 107 degrees. That was our logic that took us to 107 degrees. Now I take this molecule where I have a central atom that has an 8 valence desire for its central atom, so 4 connecting points, but it only has 2 atoms connected and 2 unpaired or unbonded paired unbonded electrons. What's happening now? If this single pair pushed more against the bonds, what do you think is happening here? It's pressing even more, right? So the bond angle here is 105 degrees. Doesn't sound like a lot, but it really matters. Okay? We've gone from a tetrahedron where the angle is 109 to a pyramidal where the angle is 107 to a bent, which is called a bent molecule, at 105 degrees. Okay? So the bond angle between these 2 bonds here is 105 degrees. Are you expected to draw a Lewis diagram, then draw a 3-dimensional VSEPR, and then tell me the angles? Yes. Yes, you are. Okay? So whatever's so funny about this, I hope it's worth being able to draw the VSEPR and use the logic of how to get there. A central atom with a 8 valence electron desire with 2 bonded molecules and 2 unbonded pairs push away and form a 105 degree angle. And the example of that is water, often called the Mickey Mouse molecule, right? Central with 2 ears and 2 unbonded pairs. Now, if that's the pyramidal, or excuse me, the tetrahedral goes to the pyramidal, goes to the bent, what do we have if we take one more away and put an unbonded pair in there? We've got just two atoms hooked together, right? And we'll get into that in a minute, but that's just a linear, a straight molecule, 180 degrees between the bonds, but we'll be there in just a minute. So in terms of a central atom with 4 connecting points, an 8 valence desire, 4 of them tetrahedral is the shape, bond angle 109 degrees. For 3 atoms, it's 107 degrees, called a pyramidal. And for 2, it's 105 degrees. It's called a bent. So those explain the 3 geometries that are based upon a tetrahedron. Remember, your molecule is going to be based upon a tetrahedron if the central atom has a valence desire of 8 electrons, because it has a opportunity for 4 connecting points. And if you connect with 4 atoms, it's a tetrahedron. If you connect with 3 atoms and an unbonded pair, it's a pyramidal. If you connect with 2 atoms and 2 unbonded pairs, it's a bent for 109, 107, and 105 degrees, respectively. The next are simple, okay? The next one we're going to look at is not based upon a pyramidal. You see the example molecule they use in the book here. It's a CH2O. Or not, maybe not in the book, but in my notes. CH2O. Let's draw the Lewis structure of CH2O. Looks like H2O, but throw a carbon in there. 514? Okay. Figure 514. And so you'd see in there that we're going to have a carbon double bonded with an oxygen and 2 hydrogens. Okay. Now, in the book, do they use the 90 degrees or do they use the bent like this? How do they draw it? They show it both ways, don't they? Okay, good. So let's draw it from a, if we were building our Lewis structure before, we had a carbon. Then you probably go symmetry, 2 hydrogens. Let me put them on both sides. H, H. They're going to bond. They're going to bond. O, let me put it here. O. But it had 6. Oh, I've got an extra one here. I've got an extra one here. Let me do that. There's 2, 2, 8. We're good. 2, 4, 6, 8. We're good. That would be a 2-dimensional Lewis structure. Okay? Welcome. Thank you. So our 2-dimensional Lewis structure looks like this. But now our concern is, and you can perfect this in your 2-dimensional Lewis structure, but the difference between a 2-dimensional and 3-dimensional Lewis structure in this case is minimal. It's minimal. Let me get you to look at this in my 3-dimensional model. Okay? Here is the model for what we've got on the board in 3 dimensions. Now, when you're drawing your VSEPR diagrams, your 3-dimensional structures, a double bond does not have any more repulsive force than a single bond. Okay? So it's not like this is twice as strong as this. They're all going to be equally repulsive. Okay? Now, when I take this in 2 dimensions and I try to push every atom, or every bond rather, away from each other as much as possible, do you see that it's going to become that? Hopefully you'd see that as these 3 angles, think of it as a wheel with a hub and spokes. Every spoke wants to get away as far as it can from its neighbor. How far apart are they going to be? Well, if you take your 360-degree circle and divide it into 3 pieces, each piece is 120 degrees. Right? But the beauty of this is there's only 3 connecting points being used for my central atom. It has a valence desire of 8, but it has a double bond. So now there's only 3 points of connection. These 3 points of connection, as they repel each other in 2-dimensional space at 120 degrees, there's nothing that needs to come forward. If any one of these atoms were to move forward slightly, it would immediately be repulsed because of the pushback from these 2. And so this atom forms itself in a perfectly, it's flat in terms of its bond angles. It's still three-dimensional because each atom has three-dimensional space, but it's flat. So even in 3 dimensions, this is your three-dimensional diagram for this molecule. There are no bonds coming out of the board. There are no bonds going back into the board. All 3 bonds are flush with the board. Every one of these angles of separation then is 120 degrees. Every one is 120 degrees. None of them come forward. None of them go back. It's 120 degrees. No. I mean, there's no way of showing, there's no darkened triangle bringing it forward. There's no dotted line taking it back. We just draw it just like this. Perfectly 120 degrees apart in a flat plane. This is known as a trigonal. A trigonal. You might call it triagonal, right? A triangle. So it's a trigonal or trigonal. Nothing coming forward, nothing going back. It's flat. Sometimes called a planar trigonal because it lays in a plane of 120 degrees. Now, if I were to take this, we can go to the next level, take my trigonal, and remove one electron bond and put an unbonded pair. Ah! The world's ending. Okay. So, just think with me logically. If I have 120 degrees apart, but then I go and I replace one of the bonds with an unbonded pair, what's going to happen? What's the net effect going to be on my geometry? These 2 bonds are going to be pushed towards each other because this unbonded pair pushes stronger than a bonded pair. So it's going to decrease that geometry there. We'll pick it up there tomorrow.